Hi and welcome to Geeks for Geeks. Today we would be discussing yesterday's problem of the day, that is delete a node from binary search tree. This question appeared in Acolyte, Adobe and three more companies. This is a medium level problem. Now let us move to the problem statement. We are given a binary search tree and a node value x, and we need to delete the node with the given value x from the binary search tree, and if it is not present, we won't make any change. Now, binary search tree follows the pattern that its left child would be having a value less and right child would have a value more than the root. Okay, now that you have understood the basic of it, let us move forward. Now to remove a node, there are three cases for this. The first case is that it would have no child. Simply it means that it is a leaf node. The next one is that it would have one child. Okay, and the third case is that it would have two child. Okay, now there can't be any other cases because the binary search tree can have at most two child. Okay, fair enough. Now we would first solve for the first case. If we talk about the first case, suppose it is having no child, suppose we want to remove this one, okay, this one. So we would simply remove it and whole binary search tree won't be affected and everything would remain same. Okay, now suppose we have one child. Okay, so we have, let us draw a binary search tree with one child only. Okay, suppose this and then this, suppose this. So this values needs to be removed. Suppose we want to remove this value and this value has one child. So what we can do is, suppose this is x, this is y and this is z. So we know that z is less than y and y is less than x. Okay, so even if we remove this y, then still the z would be less than x and it would still lie in the left side. So we can see that this can also be done. How? We would just mark this of it and we would return this. Fair enough. Now, what would be about the third case? The third case is the case where we need to think about a little bit. Okay. Now, third case is kind of very easy. The approach, recursive approach, what we would do is, suppose this and then this and then this, suppose this and this. Okay, and we need to remove this one. Now suppose we want to remove this one. Okay, we know that this side would have a value greater and this side would have a value smaller. So what we can do is, if we just remove this value, we can make this value go to this value. Okay, then we can remove this value. Fair enough. We would do just like I drew. Okay, now removing the leaf node is very easy. Just like we thought that just remove the connection. One child is also very easy. We would just attach it, and this two child, what we would do is, we would go to the left hand side, right hand side of it, and we would find the smallest element of it and we would make it as the parent. Okay, just not the parent, we would just, what is being replaced, we would just replace it with that. Okay, and the same idea would be used in recursion. Now recursive code, when explained, it is little difficult to understand. What we would do is, we would first implement it live and then I would do the dry run of it. Okay, fair enough. Let's start the implementation. So what are the implementation consist of? The implementation consists of writing the base case. So base case would be nothing, as most of the tree problems have. If root is equals to null, return. That would be just the base case. Here the return has a value, so we would just return root only because it is null only. You can either return null or you can return root. And the next case is that when it has one child, so we would see if the left side is null or the right side is null, we would do accordingly, and about the two child. Now let us start implementing this. Okay, so as I told, the base case, so if root is equals to null, we would just return the root. Okay, then there are two things that I want to do. I would first copy this because I would be using this a lot. Okay, and then I would making it small x because I'm just more accustomed to do it. And there are two cases to it. Okay, one is that if, okay, if x is less than the root dot data, then we know that it would be on the, it would be on which side? Which side? Suppose x is small than the data, so it would obviously lie on the left hand side because left hand side has a value less than that. So root dash left will be equal to the delete node, okay, and then root dash left and then the value. So we would simply say that yeah, this value is not present here, so just go to that side. So what can be the other case? The other case is such that it is greater than root dot data. Okay, so we would just write else if x is greater than root dot data, then we would do what? Root dash right is equals to delete node root dash right dot x. So we would just say that yeah, go to the right hand side and you would find that. Fair enough. Now what is the else case of it? That we have found the value. Okay, so if the value is found, we have two things. First one is that it has either left child or either right child. So if root dash left is equals to null, fair enough, what we would do is we would return, okay, we would just return the right hand side, root dash right, okay, and then else if root dash right is equals to null, then return root dash left. Okay, so if the right side is null, we will return the left side. If the left side is null, we would return the right hand side. Okay, fair enough. And now if the both the cases are not null, we would first find the lowest value on the right hand side. So we would just write, which would return me the node. So node star, just we can write suc, and then node star root, and then what we can write is while root dash left is not equal to null. Okay, then root is equals to root dash left, and then at the end we would just return the root itself. This would find me the lowest, okay, the lowest value which is just greater than that. Fair enough. So what we would do is node star temporary is equals to SUC of root. Okay, this would return me the node, and then root dash data is equals to TP dash data. So this is now again done. The swapping thing is done. Now we would delete what? The lowest one. So what we would do now is equals to root dash, we would find on the left hand side, right hand side. We went in the right hand side and then found the leftmost. Okay, then we would do is we need to update the right hand side. So root dash right is equals to delete node, then root dash right, and we know that we would find this value in this side only, that is root dot data, which is now assigned to the root, and we want to delete it. Okay, then we would return the root itself after this thing is done. Now let me just check if I made any errors which are visible as of now. So this would find the successor root dot left is not equal to null, and then root is equals to root dot left. We would go on the left hand side and then we would return the root, the lowest one. If root is equals to null, we would simply return. If the value given is less than the root data, we would simply tell yeah, update the value on the left hand side. Fair enough. If the value is greater than the root data, we would know that we need to update the right hand side. Okay, and if we have found the value, then there is one case that root dot left is equals to null. So if the left is equals to null, we would return root dot right. If the root dot right is equals to null, we would return root dot left. Fair enough. And then we would find the lowest successor on the right hand side. We would assign its value. We would update the root dot right by using delete node, and the updated value is now swapped. After the swapping, we need to delete on the right hand side. So we are doing the deletion here, and whatever is returning, we are updating here, and then we are returning the root here. Let us check for the sample input. Hope it's correct, but I might encounter. Yeah, let us submit now. And yeah, the problem is solved successfully. So that's all for today. Thank you and have a nice day.